Okay. What we're looking at here is practice 1, number 23. And what we're going to be looking at is Kepler's third law in this case. And what we have is on the Apollo missions to the moon, whenever we're at the moon, the command module orbited at an altitude of 110 kilometers above the lunar surface. What we're looking for is how long did it take for the command module to complete an orbit. So let's just draw a quick little picture here. Here's the moon, spelled M-O-O-N. And we actually have a command module up here. And it is orbiting the moon. Okay, it's going around and around the moon. Buzz and Neil are down here hopping around, falling and stuff. But their module is back up top. And it is at a distance of 110 kilometers. We could write this as like 110,000 meters in that case. Or we could say 1, 2, 3, 4, 5. 1.1 times 10 to the 5th meters. We also know that the moon itself has a radius. Let's see if we can solve our helpful little sheet here. The moon itself has a radius of 1.74 times 10 to the 6th meters. And what we're trying to figure out is how long did it actually take for the command module to go around here. And since we're looking for a how long, we're looking for a time. And because this is going around and around and around and around and again and again and again, that time is repeated, and it is actually the period that we're looking for. So if we go to Kepler's third law is that the period squared is equal to 4 pi squared r cubed if we're in a full circle. If we are in some sort of ellipse, then this r would switch into an a for the semi-major axis, divided by the gravitational constant g and the mass of the system here. And in most cases, our orbiting bodies, such as the small little command module, is such a less mass than the mass of the moon that we just consider what we're actually orbiting around, which is the moon. But if we had like 2 suns going around, we'd have to add their masses together there. Okay, so this is technically the mass of the system. If we're looking for how long, then we're essentially just plugging in 4 pi squared r cubed, where this r is this total distance from the inside all the way out, divided by g and then the mass of the moon, and then taking the square root of that. So the period is going to equal 4 pi squared, and our radius here is the radius of the moon plus the 1.1 times 10 to the 5th, which we could actually write this as 0.11 times 10 to the 6th meters. If I move this over, that'll become a 6th. And 0.11 times 10 to the 6th plus 1.74 times 10 to the 6th is just 1.85. We can just care about the numbers here. So that's 1.85 times 10 to the 6th is the total distance, cubed, divided by g, which is 6.67 times 10 to the negative 11th, and then the mass of the moon, which from our little handy equation sheet is 7.35 times 10 to the 22nd. So 7.35 times 10 to the 22nd. And this is all to the 1/2 power because we need to take the square root of it. So at this point, we know our answer is going to be 7,100 seconds approximately. Let's see if we can shove that into the calculator and get something out of it. Whenever I throw things into the calculator with Kepler's third law, because it can be a pain, I actually like to start here with the cube because that's going to be it can mess a lot of stuff up. So let's just take 1.85 times 10 to the 6th, hit enter, and then to the 3rd power, so that's a little caret cubed. So I get 6.33 times 10 to the 18 times 4 times pi, because that's like pi squared. And I get 2.499 times 10 to the 20th. Let's divide by g, so divide that number by 6.67 times 10 to the negative 11th. I get 3.74 times 10 to the 30, because I'm dividing by a negative exponent. I'm actually getting a larger number. It's like dividing by a decimal. And then we'll divide by the quantity of the moon, 7.35 times 10 to the 22nd. And all of this here gives me 509,872,68.79. But remember, we need to take the square root of that. So we take the square root of that prior answer, we hit enter, and we get 7,140 seconds, okay? Which is the 7,100 we're looking for. Remember, this is in seconds because whenever we have meters and kilograms, our time will come back in seconds here, so our period will come back in seconds. If we did this in more Earth-centered and Sun-centered units, then they'd come back in years, but we didn't do that in this case. We did it in seconds, and that's it. Really what matters here is if you can get this set up, then you're a hero. The rest of this is just left to your calculator to start churning through, and if you can do that, then you're victorious. So with that, this problem is finished. Take it easy.